I'm Tim. This PCB Sync.
In this video, we'll take a look at a real open source SMD antenna PCB to see why engineers evaluate Rogers' RO4003C in 5G microwave and some mmWave antenna designs, and which parameters need to be redesigned when switching to a different high-frequency board material. High-frequency antennas have specific requirements for PCB materials, mainly focusing on dielectric constant, dielectric loss, and parameter stability. The process dielectric constant of RO4003 is 3.38, with a tolerance of plus or minus 0.05. For transmission line and antenna dimension design, Rogers also provides a design dielectric constant of 3.55. Under actual conditions at 23 degrees Celsius and 1 GHz, its typical loss factor is 0.0027. A lower DF helps reduce energy loss in the dielectric, while a relatively stable DK helps control the antenna's resonant frequency, feed line impedance, and consistency in mass production. Let's take a look at this patch, folks. On the screen is a schematic diagram of an open-source patch antenna structure. The large rectangular copper area on top of the PCB is the main radiating structure, and the bottom connector is connected to the antenna through a relatively long microstrip feed line. On both sides of the feed line, you can see many rows of grounding vias. These vias help connect the upper and lower reference grounds and restrict the return path and edge radiation near the feed line. In this kind of antenna design, the patch size, feed line length, feed line width, dielectric thickness, and material decay all affect the final resonant frequency and input impedance. Therefore, printed circuit board traces and copper shapes are not designed or laid out in an arbitrary fashion. They're actually integral components that form the antenna's entire electrical structure. Suppose this antenna was originally designed using standard F24, and now you want to switch to RO4300. You can't just swap out the material name and keep all the dimensions the same. First, we need to recalculate the size of the radiating element, the effective wavelength of the antenna, and the material decay. After the decay changes, the required patch length and width to achieve the same operating frequency may also change. Second, you need to recalculate the width of the feed line, which is the width of this line. The feed line impedance depends not only on decay, but also on the dielectric thickness, copper thickness, and line width. Even if the target is still 50 ohms, after changing the material, the board thickness, and the original line width may no longer be usable. Third, you need to check the feed position and matching. The feed point of a patch antenna affects the input impedance. After changes in material and dimensions, both the structure of the feed point and the length of the feed line need to be readjusted. Finally, you still need to confirm the resonant frequency, return loss, gain, and radiation pattern through electromagnetic simulation and physical testing. You can't just rely on theoretical formulas to go straight into mass production. Next, let's take a look at the RO4003 datasheet. According to official information, RO4003 lists cellular base station antennas as one of the typical applications for the RO4000 series. For high-frequency antennas, lower dielectric loss helps reduce losses in the feed line and substrate, but the final antenna performance is still affected by factors such as copper foil roughness, surface treatment, connectors, radiating structure, and manufacturing tolerances. Decay stability is also very important, as it helps reduce resonance frequency and phase deviations between different batches of boards, but it alone can't guarantee the antenna's radiation pattern. The radiation pattern is also related to the ground plane, feed structure, installation environment, and array layout. In terms of manufacturing, RO4003 can use a production process similar to F24 and does not require the special treatment needed for PTFE material knives before metallization. However, in actual production, it is still necessary to customize drilling, lamination, impedance compensation, and profiling parameters according to the material's characteristics. To sum up, the value of RO4003 is not just a lower DF number, but the balance it achieves among high-frequency electrical performance, decay stability, manufacturability, and cost. For 5G base station antennas, microwave antennas, and some higher frequency designs, it can be considered as a candidate material, but the final selection still needs to be based on a comprehensive assessment of operating frequency, bandwidth, antenna efficiency, board thickness, copper foil, flame retardancy requirements, and cost. If you were designing a Rogers high-frequency antenna PCB, PCB-CNI can assist you with material recommendations, stack-up evaluation, impedance checks, DFM review, prototyping, and mass production. Scan the QR code on the screen and upload your Gerber files to start your inquiry. If you found this content helpful, feel free to